Dear audience, dear audience, session 4 is starting, and Oleksandr Korniienko will open this session with the topic of enhancing grammatical error correctness, the efficacy of large language models in error correction task. And he's supervised by Kostiantyn Omelianchuk. And yeah, Alexander, the stage is yours. Please.
Hello, everyone. Thank you for coming. Thank you, organizers, for make this chance to be here and present my work. So I hope you will enjoy, and very hope you will have questions and we can discuss. So yes, my work was under supervision of Kostiantyn Omelianchuk, who is working as well on the in Grammarly on this task. And yeah, so we are trying to uh, use large language models for grammatical error correction. And our next plan is consists from several things that I'd like to present you. So the first I describe the motivation, set the goals, also describe approach to the solution, and finally so present some results, early results that I got until now. So motivation. So in this fast changing world, clarity and grammatical correctness is one of the key factors in a people communication, and we should and to make people understand each other, we need to provide them the instrument that just make this easier. And also this especially for the people who are not the native speakers. And also in this world, we need to present something that will be very useful and very smart. So this research addresses the problem of grammatical error correction because it's not new topic, and it came from early 80s, maybe earlier, and nowadays we still have this issue, and because no one stand up and says that okay, we've got the reasonable results, and so we beat this problem. So nowadays we have a lot of benchmarks, data sets, and every time new papers released to describe their own approach to this problem. So that's why in this boom of the large language models that can provide very intelligent writing assistants, and we need and we would like to investigate their capabilities, especially in grammatical error correction task. And at the same time, we are going to investigate and provide the people the recipe of how to tune the large language models to make this task better, even the bit state of the art in the field. To evaluate our model and our approach, we would like to we are use two maybe the most common methods. The first one is a max match approach that is based on calculating the precision of the prediction that was made by the model. So, and it calculates with using true positives. That is, if model produce the same output as we expected, and this expectation is exists in a data set as one of the reference. So data set has a few references. In this case, this is considered as a true positive. In case of the true negative, it's when the model doesn't produce anything. So false positive, if model produces something that was not that shouldn't be done, for example, so it changes the word and introduce another word or whatever. And true and false negative, yeah. false negative if the model if model doesn't present anything, but we have something in references. So we need to do this correction. People, so researchers in the world use this, the F0.5 score as one of the metrics that correlates with the human judgment in the field. And so all benchmarks we can open in a GEC task primarily shows this number. As a benchmarks, we used two things. So, and let me also, yeah, we use two things. The first is a Korniienko 2014. It's maybe older version of the benchmark. It uses with this max match method of the evaluation. So it goes together, and people are describing their performance in this way. And another one is the errands that I forgotten to say. So it is very similar to the max match, but it's also considering into account the type of the error. So it's pretty the same, but there is some differences. And yeah, the main challenge in this main challenge that uses this errand method is BIA 2019. That is newest one, and the main things and important thing here is that the test set is hidden. So that makes this task make this task a little bit more clear to everyone, because we do not fit onto the test set. As the data sets, we are going to, so there is a bunch of them, but we, after the investigation of the recent state of the art approaches, we selected 3 of them. And this is C-lang. It's the most largest one, and it consists from the synthetic and as well as human annotated pairs of the sentences. The knuckle is maybe the one of the classic. So, and it was it contains as a part the Korniienko 2014, and another one is write and improve data set with a hidden test set. We select several approaches, so several families of the approaches for this problem. So it's a sequence to sequence, sequence to tag, and we also select a new one. We think that is based on the LLMs, because it has its own specific. Regarding sequence to sequence approaches, it's most straightforward, because it really requires only the pair of the sentence, parallel corpus, source corrupted with grammatical errors, and also fix the sentence or texts with grammatically correct. With advancements in neural machine translation, so this and with use of the transformers, we can use one of the approach that is presented in the model zoo. So, for example, for translation from one language to another, and can fine-tune such models to perform this task. But this family of approach has its own limitation, because the first is maybe the most crucial one. It inefficiently generates output, because of high overlap between input and output. We just need to copy input tokens to output. That takes a time, and it's not cost effective. Another one limitation is that such approaches do not provide any reasoning of such edit. So we cannot explain why we do this. And for example, for some text adjustments, we should provide people what we suggest to do. For example, fix a comma, or maybe fix some type spelling issue. And maybe the last, but the important thing is that such approaches requires a really huge amount of data. Here I mean about the order of 10 million or even 200 million of pair sentences. pairs of the sentences to train the current SOTA approaches. To resolve some limitation of the sequence-to-sequence approach, sequence-to-tag approach was presented with one of, and maybe one of the familiar, the most familiar approach in the field is a Gector. The idea is here we do not need to, we provide for each token in the input sentence the tag, whether we need to fix this token or keep it. And we also, additional to this, we can provide to what we need to fix this issue, for example, replace the input token, as well as we can, and as well we can add the replacement itself. So the main benefit of this approach is that we need we have the explanation of the edit out of the box. And another thing that we can do this text adjustments with several different approaches that can work with this framework, and we can score the suggestions and select the best one. This is one of the idea of the model assembling. And but still, this this family of the approaches has its own limitation. And one of the things that maybe the less crucial is we need the post-processing, because we do not have the human readable output, and we need to do some post-processing in algorithmic way. But maybe the one of the things that also presented on this slide as the architecture of the Gector is that we need this kind of these approaches work on token level. And sometimes to fix the grammatical error, we need to do several fixes instead of one. For example, in the example, I believe you will see this. So for example, in the as presented on the slide, so to fix the ears by ear as a correct one, we need to do two adjustments. We need to remove the S at the end of the token word and also append the prefix. So that's we need two operations. That's why we need to do in iterative way these fixings. So that's additionally computational resources, but still, so that's how does it work. Also, it's unclear how to embed this approach into the LLM framework, because we don't really understand how we can predict with the LLM the tag and other required stuff. Because but still there are a list of the recent papers that can that shows how can we approach this problem with the LLMs. So the first, we understand that the large language model doesn't need pretraining, because it's very smart to understand the human task. We can just ask it to fix the issue, and it can provide us the corrected sentence or text. Another one thing that also in one paper, authors proposed approach to produce the edit spans that is kind of the text. It produces the number of tokens, which one we need to fix, and also to what token we should fix it. So that's probably something that we can also do with the models. But still, the large language models are pretty low in performance, and the quality, as we will see on the next slide. Okay, on the next slide, has pretty low numbers in terms of the metrics that I talked previously. So as we see here, so decoder only models, it's LLM, it's our LLMs that I found on the literature investigation. So the first is that the zero-shot approach that doesn't require model fine-tuning produces pretty low scores. That's mostly because the F0.4 is a precision-oriented, and models, large language models trained to rephrase the input text, not just correct the precisely each token. That's why we have pretty huge drop in this score on both things. As well as for ChatGPT is GPT, the GPT-3 previous version, so it also has pretty low numbers. Another limitation and maybe lack in the literature is that all works that I found describes how to resolve this problem with Llama. So they doesn't try any other open source data large language models. That means so we do not have understand how we can approach with others. Maybe others perform better than Llama. And the last but not least is that there are no any work that uses the large language models to ensemble their outputs. Maybe, and as we see on this graph, the most sought results perform on the ensembles. So that's three things that we just found on the literature. That makes us a lot of questions, but three of them are presented here as our research questions. The first is so how we can improve the large language model in GEC task and provide researchers the recipe what to do and what to try. Also, we would like to test if this recipe we checked works as well for the open source models. And the last thing that we would like to see how we can ensemble the large language model, because we also see some promising results from other fields like chain of thoughts and other things that can be also used here to improve the performance. We follow the scientific method, empirical, so we just ask some questions, for example, about what data to use. So do the hypothesis and verify this hypothesis and provide, so document the results. So the first approach is so what we would like to do. So the first, we would like to investigate Llama 2 model. And here we see two things to try. So the first is zero-shot prompting. That means so we need to just find the proper prompt that does what we ask the model to do, to fix the grammatical errors in a text. And the second one is the most promising we saw from the previous slide. So some model fine-tuning improves the quality of the large language model because of instruction alignment. So we just explain model what to do and what not to do. And here we would like to vary it with the data, because we saw a lot of different data we can use here, and we should be very precise and very data efficient in this way, because it's very costly to train this model. As well, we would like to try different model size, vary it with different pre-trained models, because some large language models are released in two versions: chat version that is oriented on the interaction with the user, like a chatbot, and another one is a just basic large language model, and some fine-tuning techniques. Another things that we would like to try is to having this approach we investigated on a previous way to train open source models and check how other models performs on the same setup, to prove that this recipe is working for other models as well. And here for the zero-shot prompting, it's more clear, because we can use here any model we can infer. So and here we can use ChatGPT as one of the proprietary model V2. But also we need and we should investigate the supervised fine-tuning, and here on the open source models available for this. Here we just see the Mistral and Gemini, one of the candidates, so to try. And the last thing that we would like to check here is we would like investigate the ensembling of the models, how we can approach this problem. And here we see two things to try. The first is the ensemble just model outputs and find the best. So it's maybe the most straightforward. as it was done for previous researches with other models. And so having the best output, we can just score it and provide users the best. But also we can use the LLM as a scorer. And that's something that was not investigated until now, and we would like to test it and to see is it capable and how it perform on this task as well. Regarding early results, so what we did until now, so first, so we experiment with different data sets, and here we see that the right and improved data set is seems to be the most clear because it provides the highest recall from the list of data sets we tried. At the same time, we see that highest F0.5 score also for this model in the setup of the single model training, model training on a single data set also performs the best. But at the same time, the best model we get was achieved on the, was trained on the data, on the combination of data. That makes us to some conclusions because we still do not see the good setup of the data set, and we need to investigate it. At the same time, the best model we trained was trained on the combination of all data sets. That's some preliminary results here. Another set of experiments allows us to understand how the models perform depend on the model size and on the type of the tuning. So the first is that the bigger model is, the better result is. So it's very clear, and so we just proved our initial understanding of this. And the second one is also mostly not surprise for us, is that if you are using the chat version that adapted to interaction with the user and explain a model what to do just to fix and add the prompt fix error correction, this setup performs the best. And yes, so according to this table, so what just explained on this table. To conclude, so the first, we confirmed some observations and findings from the paper related to the GSC in the field. And the another one that the trained model we've got is very comparable with other single model setup systems. But the main benefit of our approach is that we use in orders less data to get this model. Yeah, that's all. Thank you.
Thank you, Oleksandr. Any questions from the audience? Or oh yes, one hand raised from Zoom. Mariana, please.
Yeah, hi. Thank you so much for the presentation. It was interesting and the problem is super clear. My question is, why did you decide to do all this for the English language? There are so many solutions for the English language, yet you could have done that for the Ukrainian language, where we also have a benchmark, and there are some large language model solutions already that you can compete with. And yeah, so why was the choice of the English language?
The choice was that probably we have pretty strong candidates here, and we would like to beat the sort of the, let's say, of English world, of the English speaking world here. But Ukrainian language is one of the candidates for the next iterations, and probably when we just find the clear recipe of how to tune the model on the English, I believe that this could be also applied to the Ukrainian, and we can check how this recipe also works on other languages. The main problem, maybe, so I can just, it's something that I believe is that current large language models are not well trained on the Ukrainian. So, and we need to do some homework before model start understand better the task, and after we can just do this. But that's my own feeling, and we need to test to set the hypothesis and to understand how we can what the problems will be and how we can overcome them in the future. Thank you. Thank you.
Thank you. I would really much like to see the continuation of this work.
Me too. Thank you.
Adam?
Thank you for a great talk. I would like to ask you to go back to your slide number 5. Yeah. Bullet number 2. I'm curious, what do you mean by saying a recipe here?
By recipe here, I'm trying to say what techniques and what parameters we should use to train the model.
So to really mean configuration?
Configuration, right.
Why just using or adopting a term from either culinary or pharmacology to computer science talk? I would rather suggest you to do that not in a presentation at professional audience. One more question is on slide number 6, please. You didn't mention, and please excuse me for my ignorance, do you mean sentences in the header of the column number 4 in your table?
Yes.
Okay. And it says 6. It is perhaps and possibly in the brackets somewhere in one of your slides.
Yeah, here.
Yeah, here. Does this mean that you didn't check that by saying perhaps?
Yes. So we are not really sure. So here, and we would like also to test it first. So, and also the first perhaps that's I used it because from the next slide we will see that the fine tuning really requires to improve the GC, but model can do this.
It needs to be pre-trained or fine-tuned.
Yes, yes, that's
both.
That's the first thing that I try to explain. So we just say this, but think this, but from the numbers we cannot say that in 100%. So that's the first.
Yeah, and
unsure.
Possibly that means that you are a little bit more confident.
Maybe confident, maybe less confident. So here I also have some, we had some experiments with edit span prediction. So we tried to reproduce results from the work and we failed with this.
Okay.
So, and that's why researchers saying that they can do this and we have pretty nice results. Where it is? Here. Very high number, but still we tried to do this and we failed with this. That's why I mentioned so as a proc, but still that's something that was not unsure, especially for me.
Yep, thank you very much.
Thank you, Oleksandr, for the presentation. Okay, I think we can move on to the next speaker. And the next second presentation in the 4th section of the today presentations will be presented by Ihor Kosovych, who is supervised by Yevhen Kostiuk. And the topic of their project is evolution of topics in Ukrainian Parliament from 2014 to 2023. Yeah. So I think we can start as soon as Ihor sets up the presentation. Oh, Ihor, stage is yours.
Hi, thank you for the presentation, Ruslan. So my topic, as it was mentioned, is evolution of topics in Ukrainian Parliament from 2014 to 2024. It is it is work in the scope of my diploma, and I am really appreciated the advice by Yevhen Kostiuk, which helped me a lot with his ideas, with his advices, with his help. So thank you. Now we are going smoothly to the plan of our presentation. And first of all, we will focus on motivation and research goal. Then we will go to related works analysis, research questions, data, solution, evaluation, and finally to the early results. So what is hidden on the motivation part? First of all, in the last almost 10 years, a lot of happened in the Ukrainian society. We had revolution of the dignity, we have annexion of Crimea, we have a lot of reforms which were applied in politics section. We had COVID period, we had the start of the Russian full-scale war. So there are a lot of happening during last decade, and it is really important to understand how is moving parliament with all these changes that is happening at a real time, because we need to understand the direction, how we are evaluating, how we are improving ourselves, and in this with this track, we will be able to understand like modern problem in our real life. Also, we need to understand like these changes which happening and the reflection of the politics, how they are adjusting to this all problems. Based on this, our research goals are to uncover topics evaluation using parliamentary transcripts, and based on this information, we will provide a detailed overview of Ukrainian parliamentary discussions based on the data which were published on the Verkhovna Rada of Ukraine website. And also based on these topics which we will be able to extract, we can reveal shifts in this Ukrainian discourse in parliamentary discussions, which we can determine how like are they representing our needs or not. So in the related work section, I was mostly focusing on something similar, but not also something similar. The work of Taran was related to the Ukrainian political discourse study, but it was corpus-based approach. And she focused mostly on analyzing the pronouns and grammars and slangs in the Ukrainian discussions, but not topic extractions here were applied. In Kanishcheva work, there were applied really huge work because they were focusing on the last decade, almost last decade of Ukrainian parliament, and their topic was bilingualism in the Ukrainian parliament. But still, no topic extraction were mentioned in these works. And based on this information, the research gap are the next: lack of topic analysis in Ukrainian parliament and what happened in after post-2014 Ukraine's parliamentary discussion, because we need to understand all this question, all these gaps, and to fill it. Based on this, we had a proposal to analyze evolution of topics in Ukrainian parliaments during almost last 10 years. So the research questions are pretty simple. How the topics of discussion within the Ukrainian parliament evolved from 2014 to 2024, and how can NLP techniques enhance this analysis? Because to understand topics in a non-English context, especially in politics, can be a really not trivial task. For this kind of task, we are using data which are publicly available in the site of Verkhovna Rada of Ukraine. This is stenograms of all sessions which were publicly available. They are stored in PDF format. Total amount of all sessions that were downloaded is 946. Yes, so it was all transcripts that happened during this period of time. Now let's go into the distribution of sessions. Let's imagine that for some short period of time we skip processing part, and currently we want to understand what is like really distribution of the data and of the sessions. Here we can see that in summer period we have decrease of sessions. It's logical because in this period it's general tendency, mostly like a trend, that a lot of workers are going to the vacations and to refresh, to have a rest. And due to this tendency, we can see that in June, July, and August, it has a really small amount overall of sessions. But on the other hand, on December, it is the end of the year, and politics also want to, in a rush, maybe to finish some task, to finish some bills to accept it. And they decided even sometimes working in 6 days, because in this case, they were covered even Saturdays for their work. Based on the statistics, what we have in this data, as I mentioned, we had 936 documents in PDF formats. Total amount of words in this documents is approximately 11 millions of words, where the unique words are approximately 300,000 of unique words. Mostly occurred word was mentioned was Ukraine, approximately 200,000 times it occurred. The next neighbor to the Ukraine is Proшу, please. It was mentioned in less than twice amount less. And the third one is the word colleague. Yeah, so basically what is like the full approach of all this work? As I mentioned, we had this PDF documents. What is doing after that, after the collection process? We are converting these PDF documents using PyPDF framework into TXT format. Then we are cleaning this data, removing headers, footers, a lot of spaces which are making a noise for the data. Also, we are removing stop words. In Ukrainian, it is a list of Ukrainian words which was taken from Korniienko work. Also, we increase this list of stop words. Initially, it contains approximately 2,000 of stop words, but we increased it to approximately 2,500 because we have a really specific topic and we need to include some specific stop words. Also, we are removing punctuation, and after that, we are getting this text. After that part, we applied tokenization, lemmatization, and finally we are getting prepared corpus. It was like the first flow. On the other flow, we are also getting data extraction, because it's also important to understand when session was happened. When we were applying it, unfortunately, we will not able to cover in 100% accurate date, and in 30% of files we were filling it manually, because we will not able to handle this situation. After that we have already preprocessed data, everything is clear. We are applying next approaches. First of all, we are going to apply it LDA. Next, BERT topic, which will return us the set of words specifically to the topic. And after that, we are going to apply large language models in order to combine this set of words into some specific of topic. What is evaluation under all this stuff? First of all, we will be using a coherence score to measure similarity between this set of words which are representing each topic. And also we are going to use temporal analysis accuracy as we want to compare the topics which we are getting with some social political events which happened during this year to verify that it was exactly the same and what we are getting from the model. Early results from LDA. So first of all, we can see that in first example, I highlighted the words which mostly suits better to the discussion of new bills and changes in legislation. These words are law, change, project, amendment, yeah. So it was like two changes in legislation. The other discussion was about land issue due to the words like land, area, project, and some changes. We are also going to apply intertopic distance map, where the size of the cycle depends on the total amount of words which represents this topic. And from this total amount of words, we will select which are having the most, the higher coefficient, and we will based on it, we will select to which topic this set of words are related to. So as I mentioned, like words, terms as committee, bill, project, and amendment in multiple topics underscores the Parliament focus on drafting, reviewing, and amending legislation. Also, land with policy and law points to substantial discussion around land reform. What about summary? So basically, we identified summary decrease and end-year legislative rushes. And from LDA, we identify that economics reforms and legislative process was mentioned like mostly in the 2021 year, which we already analyzed. For future work, we want to improve our LDA, also to apply per topic in order to see the results from per topic. And based on this set of words which we will get from these models, we want to apply LLMs, I think GPT 3.5, in order to get topics which these words are representing. Concluding remarks, data for the next analysis are prepared. First iterations are already implemented. We highlighted gaps and we are moving on. Thank you for your attention.
Thank you, Ihor. Questions from the audience?
Thank you for your talk. I would like to ask a couple of questions. So firstly, slide 14, you said about using LDAs for getting the actual topics. Sorry, large language models. So do you want to generate like a readable title from the keywords? Is that the intention?
Yes, because LDA, what LDA? It's a generative probabilic model, and it thought that document is set of topics and topic is set of words. And we are getting set of words per each topic. And with this set of words, we are going to LLM, and then it can combine everything into generalize some terms. Yeah, so you are correct.
Okay, thank you. Another question, did you consider using some metrics like coherence or diversity to assess topics quality? They, in my experience, don't necessarily correlate with readability, but still there could be some measurable, some measure to score the results.
Unfortunately, no, but I think we can discuss it with mentor because it's a really good point in order to increase like full list of evaluations. So it would be also nice to compare with it.
Okay, and on slide 17, you used PyLD-Viz, I believe.
Yes.
This library called. Just out of curiosity, have you tried playing with this lambda parameter to see more rare words from the topics?
Yes. So we were experimenting from, for example, 0.1 to 1. And yes, so mostly currently we are trying to adjust the best parameter for this lambda because it's really adjustable and it returns different values for us. Currently, as it's like first iteration of LDA, we are leaving like 1 for it, but nextly we will adjust it for our results.
Okay, thank you.
Thank you.
Is there a question from online participants? Mariana?
Yeah, and I see also Maria has her hand raised. Probably she has the same
Oh.
question. So this corpus, parliamentary corpus that you referenced on during your lit review by Kanishcheva is actually available via the GRAC corpus. So I was gonna ask, why didn't you use the ready-to-use corpus that is arguably already tokenized and lemmatized? And why did you have to go through all this process yourself?
So we decided that it would be better make this full steps in our work, and we will be like more reliable with the data if we are collecting on our own. But yes, so it's a good question. Good point.
Okay, my second question is, what did you use for lemmatization of Ukrainian? Like which
We
tool?
were NLTK.
But I don't think an LTK supports Ukrainian, does it?
Let me recall it.
Because there are a couple of libraries that support lemmatization of Ukrainian, and I don't think an LTK is one of them.
Yeah.
So I was wondering which one you were using.
Sorry, I cannot recall at this moment. I
All
will
right.
come back in a few minutes.
And that's okay. I'm in the chat, in the Zoom chat. So,
Okay.
and then one more question is, on this very slide, I see Верховна Рада України, Верховна Рада України. It's a multi-word expression. So I was wondering whether your LDA is word-based or multi-word expression-based.
What I didn't mention, we also applied n-grams as one of the processing steps in order because some words are mostly better to consider as like one words, as Верховна Рада України. When 3 words, we are combining it into one words, and we will see like the better results because it can split it to separate words, and it's not what we are looking about. So we run n-grams for different numbers, 3, 2, combine some obvious one into one form of the words, and after that applied LDA over it.
Okay, thank you. My recommendation would be not to glue the word together, but at least use underscores, because otherwise you can create ambiguity. And it's an important point. So it's a big omission that you haven't mentioned that you're using multi-word expressions here. So yeah.
Yeah.
Thank you.
Thank you, Mariana. Maria?
Yes, I still have one more question. I'm not a specialist in language technology. I'm just philologist. And my question is perhaps naive. You mentioned different topics on the beginning, but we do not see these topics. And on this slide, I see the words which are frequent in this text all the time, like законопроект. But is it possible to ignore these words and focus on the topics which arise in different years in this corpus?
Sorry, I didn't got. We are not getting topics, we are getting set of words. But we also can include some words, if we see that it doesn't matter anything for us, we can include it in stop list. And then when we are preprocessing the data, we will just remove these words from the data.
It seems to me that it would be interesting for me as a philologist, yes, to see what changed in this corpus during this time. Okay, thank you.
Thank you.
Rostislav?
I actually have a very similar question, because when you model topics in topic modeling, these buzzwords like законопроект actually don't contribute anything and even may distort the topics, as you have shown. You showed two topics you modeled, and the first is useless. It's not a topic at all. Certainly, Verkhovna Rada is legislative body. Its main task is to develop new legislation rules and discuss them and adopt. So this first topic is just about nothing.
Yeah, I'm totally agree with you. So currently this stop list is increasing and increasing, because even when we are adding some more stop words, some new stop words are appearing. And we are still in the process to the final version of this stop list, where we will be able to see less noise in this LDA response.
There are almost all words are very general, and they could not be and should not be used to determine topics, like Komitet, Projekt, Zmina, Polityka. It's about nothing. But probably every single speech of every member of the parliament will have these words in it. So you should see very carefully all these words.
Yeah, got it.
Yes, Mariana, please.
While we're on the topic of stop words, for what you're saying, it's sounding like you're adding these stop words manually. Am I right?
After we applied LDA, there are a lot of words which are, as Rostislav mentioned, they are not bringing us any valuable, and we are increasing the stop list, which we already have.
Yes, but it sounds to me like you're doing that manually, meaning you run the analysis, then you take top N words, you review them, you review them manually, and then you add them, decide whether to add them to the stop list or not. Is that the process?
Yes.
Okay, have you tried something like TF-ADF at least to find the most impactful words?
Nope.
Okay, I highly suggest that you stop doing that manually.
Okay,
all right.
Thank you.
Vadim? Oh.
No, there are no hands over there. So my question is about, again, sorry about that, about extracting topics from these bags of frequently used words. If we look at your diagram at the left, what would be your estimation of the number of words included in the central topic area, which is red? How many?
We experimented. We started with 10 words per topic. Then
no, just a second. This circle in the middle of the diagram to the left corresponds to how many words as a list?
Approximately more than 100 of.
I believe several hundreds.
Yes.
And then you said that you just feed it into the prompt of a large language model to generate a sentence. The topic is normally a sentence, human readable in natural language, right?
Yeah.
How would you select those several words from the several hundred words which you collected in the bag of relevant words for this area?
I think it would be better to select like first top words.
As already mentioned, those top are just the noise.
And if we remove this noise, then
and you remove it manually, as discussed with Mariana just now.
yes. So if apply TF-IDF approach as Mariana suggested, then we will remove all stop words. And in that case, we will not have this noise, and we can select top words from all this list, which we will send to LLM.
Take a look at existing state of the art in the probabilistic topic modeling and topic identification. There are several models which use probabilities and conditional probabilities to put this stuff together.
Yes, so it makes sense.
It makes perfect sense.
Yes.
And this approach is known for several years already. So please, I would suggest to pay a look to the literature in probabilistic topic modeling, also using machine learning approaches in combination with this probabilistic topic modeling. That might help. One more way to go could be extracting or discovering not just typical words or frequently used words, but the terms which are specific for this topic area.
Okay. So
and this is the next step after the stuff you have done by using an LTK or something like that for Ukrainian. Okay.
Okay.
Thank you.
Thank you.
Yes, I would like to also ask a question. Could you maybe please go back to your motivation slide? Yes, so yeah, I would ask you to explain. So I had an impression when you were describing the motivation that the motivation is pretty ambitious because you want to understand the trends in the politics, in the parliament, and how it reflects what is currently happening in the country. And how are you planning to combine this with like with topics that you will receive? Because at this point, I see that you are halfway to get just a topic from the text, but then you have to do this analysis. And like, if you have this picture in mind, I would appreciate if you could describe your plans, research plans.
Yes, so basically when we have, for example, topics per year, then we can see the shifts, how it was changing during the last 10 years. And based on this information, we are going to apply this analysis just to understand and reveal how it was changes from 2014 to 2023, because it should changes. Even right now, a lot of another sections should be discussed in parliament than in 2014 or in 2015. So it's like the main focus for us to understand how it was like changing and trending.
Okay. Okay. Thank you.
Just have one more comment to elaborate on the previous question and the way you answered. You mentioned that you understand topics as the ordered bags of keywords. So if you are successful in removing all the rubbish from the bags, then it could be more informative to compare the bags, not the topics generated from those bags, not the sentences, which are the labels for the topics, but the bags of those words, including their frequencies. And then you will see what changes in a little bit more granular form. You may build the volatility diagram, for instance. You may look retrospectively at this step. Thank you.
Okay, thank you.
I still don't understand the how can we use that out, except of pure curiosity? What information can give us the topics discussed in the Верховна Рада України? What can we do with that?
So, knowledge.
Yes, I think we are done with the questions. Thanks to the audience for active participation. Thank you, Ihor, for your question. I hope you take the comments into account and yeah, improve your work.
Yeah, thank you.
Thank you. Yes, so the last speaker of today's session is Yurii Antentyk, and he will be delivering presentation about extracting text representation from pre-trained language models via generalized Levenstein distance. Yes, and he is supervised by Serhii Havrylov. So yeah, Yura, stage is yours. Good luck.
Hello. 1, 2, 3. Yeah. Hi everybody. My name is Yurii. Thanks for staying alive. The topic of my talk is was already told by Ruslan, I guess. Before I proceed, I would like to thank my supervisor, Serhii Havrylov. Without his help, I would definitely not be standing here today. So the agenda for the talk is a brief introduction to text embeddings. Then I would like to formulate the questions that we would like to ask in research. Then we would present the chosen approach for extracting embeddings. Then we will suggest an enhancement to this approach. And then we will formulate more specific research questions, as well as define the methodology at step of the experiments. And after that, we would like to outline some directions for future work. Yeah, so just some brief introduction you already know. Text embeddings. So embedding is just some kind of a model that encodes a text of arbitrary length into a fixed vector representation. And it's important that this vector should capture semantics of the input in order for it to be useful. What can we do with them? So first, embeddings can be used as features for downstream tasks. Another application of embeddings are, for example, compression. If you need to compress some objects, then send it via network and then decompress it, you can use embeddings. And also an interesting problem for embeddings is the problem of semantic search. And in particular, the structure of vector databases, which is an efficient database that is used for this particular task. So the task of semantic search is like you have a bunch of documents and you have a query and you need to select the set of most relevant documents given to the query. If we have some embedding model, then we have a database of documents. We just embed them into embeddings, and here they are. And if we have a embedding for the query, it is simple enough to find the set of relevant documents because there are specialized algorithms that do nearest neighbor search or approximate nearest neighbor search fast enough for a large amount of documents. So some traditional approaches that were used before were word-to-vec. It worked based on a bag of words model with the idea that the meaning of the word is determined by its surrounding context, meaning that similar words will appear in a similar context. And so what word-to-vec optimized is probability of the word given context. So it's just like a dot product between the embedding for the contents and the embedding for the word itself. Yeah. As we all know, the word-to-vec embeddings employ some semantic and syntactic relationship. I guess I will skip it because it's already known. For the shortcomings of such approach is lack of contextual information, because every word has fixed embedding and it doesn't depend on the context. And we can define embedding for the sequence, but it looks like a hug because you average them all together. That's not really meaningful, so to say. Another approach is autoencoder, and it assumes that there is a latent space which the observation may be encoded into and then decoded back. And the way we train it, we just minimize the reconstruction error, and that's all. But the structure of the latent space may be not good and don't possess statistical properties, and this means that we may have a perfect reconstructor, but the embeddings don't really have any meaning in this case. One step further is variational autoencoder, which assumes that sample comes from the distribution from the latent space. And this distribution should be simple enough in order not to overfit and possess these cool statistical properties. So in addition to reconstruction error, we will have a Kyle divergence term between standard normal distribution and the distribution of the encoded sample. The pluses of this is that it has probabilistic interpretation and the mass that was worked out, and also that embedding is modeled explicitly, but as we all know, it's not really popular today because of transformers and large language models. We can also try to use embeddings directly from pre-trained language models. So for example, here is BART, and if we want to have an embedding for the word, we have the output from BART at the particular position, but again, it's not really straightforward because, for example, here you have 12 layers, and it's not clear what output to take. Do you take output from the last layer? Do you take output from, for example, 2 of the last layers? So it depends actually on the particular task, and the choice of combination of the outputs looks not intuitive. So it's look like people just pick what works best. And that's not really have any mathematical meaning behind it. But you probably also know this, but today we don't really explicitly model embeddings. We rather fine-tune the language model for each particular task, and it seems like we don't really need embeddings at all. But that's not completely true. We still need them actually for semantic search, because fine-tuning for semantic search is not straightforward. So, for example, here is a paper that tried to fine-tune for semantic similarity task, which is GPT. So what they did, they took the query, they took the documents, they encoded it via GPT. They had some kind of embeddings, and they did cosine similarity, and they trained with in batch negatives, and basically that's all. But if you have a lot of documents, then you cannot really pass like combine the query with every document, because it's like a bit time consuming. So in the state-of-the-art setup for semantic search, transformers are basically used for re-ranking, which means that the set of candidates is determined by a simpler model, which is based on keyword search, and transformers are then used to rank the lower number of documents, which seems to be most relevant. So having the way of having the explicit embeddings are still desirable in this case. Yeah, and so the question we would like to ask in this work is whether we can extract embeddings from a pre-trained language model, which may be transformer, but not really in particular transformer, maybe like any other model. So the problem is as follows: you have a pre-trained language model, you have some sentence. We need to define some kind of procedure to extract an embedding from this sentence, which should have some kind of meaning. Yeah, so, and we want these embeddings to be suitable for multiple downstream tasks, which means that we don't want to do fine-tuning, so we don't really have additional data. So all we have is a model and a sentence, and we want to have an embedding. Another challenge is that this language model may not model embeddings explicitly like it's done in transformers, so it's not really intuitive what is an embedding in the transformer, actually. And from the works that we have seen, like all the works, they either fine-tune the pre-trained transformer, or they change the architecture to somehow incorporate the embedding into the architecture of language model itself. So for example, I've seen the works that have an encoder and decoder transformer, and in the middle, they have an embedding, and attention between encoder and decoder should use only the embedding. But it means that you need to retrain the language model from scratch, and we don't really want to do this because like there is a lot of computational power related to training the language model, and we somehow want to just harvest the knowledge that is already present in the language model itself. So I would like to say that it seems like a bit of the research gap, because there are not really a lot of works on this particular topic. So like it seems like this particular question should be researched a bit more. It turns out that there are some papers on this topic, but before we do this, just a brief recap on the what is language modeling. So we are given the data set of sentences, and we want to train the language model with parameter theta, such as it maximizes the expected probability of a sentence. Basically, that's straightforward. And the probability of a sentence is just a product of probabilities of a token at timestamp t conditioned on all the previous tokens. And the way we do this, we just maximize, we just do maximum likelihood estimation, which is we just minimize the KL divergence between the probability of the next token produced by the language model and the degenerate distribution, where all the probability mass is assigned to like the next token in the sequence. That's basically straightforward. Yeah. So in this particular case, it's LSTM, and my examples will be with LSTM because it's easier to pursue. And in green is denoted the model that is weights of which are being optimized. So we came up with, we stumbled upon a paper called can unconditional language models recover arbitrary sentences, and they propose another approach for learning and embedding for a sentence for a pre-trained language model. So in this setup, we have a pre-trained language model which is fixed, so it is not being trained. And we have an embedding vector Z for our sentence. And we want to find such a vector that maximizes the probability of the sentence produced by language models conditioned on this vector Z. So we condition language model on vector Z and impose the optimization problem in such a way that we want to optimize vector Z, such as if we condition it if you condition language model with it, the probability of the sentence X is maximized. So in this particular paper, the way they introduce the conditioning for the language model on Z, they just say that Z is the first hidden state, and for every hidden state, they just add this vector Z. And basically, they do the same objective, but they now minimize with respect to embedding vector Z. So this approach has its own benefits and shortcomings. The biggest plus is that there is no need for additional data in order to find the embedding. And there is also a paper which explores similar idea for transformers. But the biggest downside for it is that for each sentence, we have a separate vector Z, and we need to solve this optimization problem for every sentence. But there might be cases when it's appropriate. For example, for this vector basis, you can just index all the documents once, and the language model is frozen, so you can use a large number of computers. The other minus is this authors report difficulties with recovering longer sequences. And the quality it needs to be further assessed. It's not really clear whether these embeddings are useful or not. Similar idea was explored for transformers. Basically, the idea is the same. You just add this vector to every timestamp in different locations. So you don't add the vector simultaneous in these 4 positions. You can just pick one position, for example, after feed-forward layer, feed-forward network in some layer, and you just add this vector for every position, and you do the same optimization procedure to find this vector. So that's also straightforward. Yes, and now we want to try to propose an enhancement for such procedure. And first, we want to identify the potential problem, which is exposure bias. So exposure bias is a problem where model is trained on ground truth data, but it has to generate its own data during inference, and the distributions of data used during training and data used during generation is different. So what's actually the problem? So for example, consider a third timestamp, and for a third timestamp, you condition language model on x1, x2, and x3, which is first 3 tokens in the ground truth sentence. But by doing this, we ignore the probability distribution of the first, second, and third tokens that is produced by the model. And there is no guarantee that this probability distribution will be perfect for the model to sample exactly x1, x2, and x3. So when we do reconstruction with this vector Z, we condition our language model in vector Z, and we sample the next token from the probability distribution. And there is no guarantee that this x hat 1 will be equal to x1. And it means that distribution of these red guys, which are tokens generated by the model condition on Z, it differs from the training distribution when we trained this vector z. And it means that we trained for one sentence, and we during reconstruction we get completely another sentence. And it means that this embedding z actually fails to fulfill its duty, because the whole point of conditioning on z is to be able to reconstruct the original sentence. Interestingly enough, this problem has a lot in common with the problem of theory of control, and but in particular the problem of distributional shift in behavior cloning. So what it means? We have an agent, for example, smart car, and it observes the state it is on, and it is trains a neural network which produce the action which the car should take in this particular step. And the idea of behavior cloning is that you would like to mimic the behavior of the human expert. So you record the actions by a human expert and you train a policy. But in reality, this policy will not work, because the trajectory will differ substantially from what the expert has done because of this error accumulation, because the policy is not perfect. One of the ways to mitigate this is used dataset aggregation. And so the idea of dataset aggregation is that basically you take this policy that was this red policy which failed to learn, and you take a human expert, and you like a human expert will provide the like ground truth actions that should have been taken, and you then combine your data set to include the red and black trajectory, and you train your policy once more. And eventually, when there is lots of data, the car will stop failing. So our task is similar in a way that ground truth sentence is expert trajectory, and generated sentence is this trajectory which is produced by the policy, and they differ, and this is exposure bias and distributional shift. So this idea of assessment of bad trajectories were also explored in NLP, and in particular, we can use Levenstein distance to mitigate this. So I guess I am low on time, so I will just start skipping the material and just move it like in a high level view. So what can we do? We can so assume you have some like part of generated sentence and part of ground truth sentence, and you don't really know what tokens should I pick next, because the generated trajectory already differ from the ground truth trajectory, and I need to come up with some kind of algorithm which will like expert algorithm which will at any point of time tell me what should I do, and this like algorithm and like policy should be like algorithmically justified. And like in this paper, optimal completion policy, they just observed that they can suggest such policy based on added distance. So so this third bullet, you can say that, or maybe not third bullet, wait, maybe yeah, maybe fourth bullet. So for the generated sequence and for ground truth sequence, we can deterministically produce the optimal next token, which minimizes the potential added distance between sample trajectory and ground truth trajectory. And that means that we can rewrite our objective to minimize the added distance between sample trajectory and between ground truth trajectory. And the benefit of such approach is that we now train on generated prefixes. So the model generate prefixes and so the model, like during training, it does not have access to ground truth sequence, which means that it is being optimized based on the tokens that it has produced. Yeah, so basically, I guess I will skip this top part with Levenstein distance and dynamic programming, which is not really which is not crucial to understand. What is crucial to understand is that for a generated prefix and ground truth sequence, we have this POC, which is an optimal policy, which will give us the set of tokens that should be produced next. And we have the probability distribution that is like that the language model gives out. And we minimize the KL divergence between this policy and the probability from the model, again, with respect to Z. And so this idea was in this paper, optimal completion distillation was explored for simple language modeling, and it has shown a boost in sequence-to-sequence task. So that's why we also hope that it will increase the quality of the embodiments. And for the research questions, like very briefly, so first question we want to ask is actually, does it really work? Because it might sound silly, but for the papers which describe the steering, there is no code, and we have contacted the authors, and they said that the code is lost. So we need to, we need to implement it once more. And and so we need some kind of proof of concept to this, and we just suggest training a reduced version of GPT-2 or LSTM language model on the language of arithmetic expressions in order to keep the language simple and in order to keep the model also simple. And given that, we will actually know whether it works or it doesn't work. It seems to be working with LSTM, but we actually struggle with GPT-2 for now. Yeah, there are some metrics which might help us assess the quality of the reconstruction quality. Basically, exact match, it means like how many tokens we have matched between ground truth sequence and generated sequence. And for example, prefix match, it means how many tokens we get right until the first error, because it was reported that when you hit the first error, the generated and ground truth sequence, they just become completely different, and that's like maybe another confirmation for this exposure bias. And yeah, and question 2 we would like to ask is how these embeddients compare to traditional approaches. Ruslan, I guess I don't have time, right? Or...
Well, we still have 3 minutes
for questions, right?
Yes.
Okay. Yes. So I will just skip it. So we have a big like we just want to take the sentence evaluation benchmark and just run this embeddings on this and compare it to just traditional approaches. Basically, that's all we want to do. And yeah, I guess I will also kind of skip it. And the last question we would like to ask is whether this optimal completion distillation that we suggest as enhancement, whether it enhances the quality of the embeddings or not. So we just take the same benchmark, we implement this enhancement and see whether it helps or not. Basically, that's all. Yeah, so current state of the work is I've done a literature review and now have understanding like of what's happening with embeddings. I have a good understanding of the math behind the proposed approach, and like basically I just explained you. I've implemented this LSTM with steering, and it seems to be working for the toy example. Implementation of GPT-2 currently does not work, and I'm in process of making overview of the dataset and metrics for the evaluation. Yeah, I guess. Yeah, so as a future work, we can just, for example, consider other distances other than Levenstein distance. Yeah, so for this to be possible, we need to in similar fashion derives the optimal policy, but for other distance, that's the main criteria. We also can try exploring the compression of the resultant embeddings, because nobody restrain us from using FP8 or FP16 or binary embeddings. And I actually think it's might be interesting topic based, because embeddings on the edge devices may be something like interesting to discover. So for example, we can just do like a binary connect, maybe somebody knows, like for this, and expand the experiment setup, because even with experiment that I have proposed, it's still not completely clear, like whether like whether it is comparable with traditional embedding approaches. Yeah, thanks. Sorry for not making out on time. I was trying my best. Yeah.
Thank you, Yura. Are there any questions from the audience?
Thanks for your presentation. Can you go back 2 slides? Start of your future. Yeah, just go back to future work. So previously you mentioned that you are looking for benchmarks for embeddings, right?
Yes.
You can take a look at the paper Massive Text Embedding Benchmark. They evaluate across a set of different tasks like classifications, retrieval. So
yeah, I think I had found a similar benchmark. I don't know if you know or not. Yeah, I maybe can find, but it's called Centival. It's also like 17 different tasks. They define the topology for the problem architectures, and also like it seems legit. Yeah, thank you for your comment as well.
It's included in that benchmark because it's really an overview paper. Like they took a set of benchmark and it's really thorough. Like they evaluate nearly 100 text embedding models across different tasks, so it would be helpful for you. And another, you seem to struggle a lot with extracting embeddings from transformer models.
Yep.
It's kind of solved problem, but you have to, I haven't seen if anybody actually measured it. Like, for example, if you could take a look into llama.cpp, it's an framework for optimized inference for language models. They added not a long time ago a method how to extract embeddings from any language models. They basically extract embeddings from every token that you inference. Then they make sum of squares, square root, and divide by. So they normalize those embeddings. I wouldn't get into specifics much, but you could get embeddings from any kind of language models, and you could actually skip GPT-2 and go to something more complex like Mistral or Llama, for example, and like use something more recent. Like I suggest for you to take a look, and it would be interesting to evaluate that, and you seem to be on a good path.
Yes, maybe one more question from my side. I'm not, I don't have much practical experience with extracting embeddings, but at least in theory, it seems to me that, for example, when we talk about BERT, then it has this CLS token that in theory should summarize the context of the sentence. Is it, I don't know whether it's a correct question, but have you tried to use that embedding as a summary of a sentence or something like that?
Yeah, it seems like this. It's not completely clear how exactly to use it, because, for example, you have like 12 hidden layers in BERT, and you can choose any combination of embeddings from every layer, and it's not clear on what to use when. And there are works that like just evaluate different combination of like hidden states in the CLS token, for example, and they provide accuracy. And for example, last 4 layers, concatenating last 4 layers gives the best accuracy, which is not clear why it is so. Because it seems like I don't know English word like a costel. For example, in Elmo, what they suggest, they have like it's an LSTM language model, but they suggest taking hidden states from all the layers and add additional scaling parameter, which is then learned during fine tuning. So it is not completely clear how to like freeze those combination of activations from different layer in order to produce a meaningful embedding that will be good across every task. In contrast, this approach, like it defines a clear mathematical foundation for what is considered best, and it just optimizes it. I don't know if I answered or not.
Yes. So actually, you kind of smoothly lead us to the next question that I wanted to ask. Do I understand correctly that the math part is kind of proved, and in theory, this Z vector should work, and you're working on a practical implementation or something like that?
Yeah. So there are like papers on this. The first one was on LSTM, and the second one was on transformer. So they showed that it is possible, and they showed that evaluating these embeddings on, for example, STS is better than using this CLS embedding without any adaptation, so to say. So it seems like it for LSTM we were able to reproduce it, and for GPT we hope we will. And so in this work we just want to like as there is no code, we want to double check whether it's a valid approach, and if it is, then suggest like this an enhancement and also see what will happen.
Yeah, and maybe one last question, like what it brings to us if we can do this Z vector estimation by different models. Why it's, for example, you made it work for the LSTM. Why do you need it to work for the transformer GPT?
I think the idea is that you have a pre-trained model and you want to extract some, I don't know, you have 10 sentences and you want to extract representations for each of them. So, in here you don't need any additional data, like apart from these sentences. So basically, it turns every like model which is not actually modeling the embeddings to model them. Like so you have a, for example, transformer which don't really model any embeddings, and you make it model embeddings by conditioning on it. Does it make sense?
Yes. Okay. That's all from my side, and I don't see any raised hands in the offline audience and in the online audience as well. And this is the sign that the first day of the Master Symposium is over. So I congratulate all the participants. I thank you to all the guests who came to listen to ask questions, and to give us suggestions. And also, I'm very grateful to our online participants for their like active participation as well. Just a quick reminder that tomorrow we will have one more session, so you're welcome to come as well. Yes, so thank you all and enjoy the rest of the day.